Hi, my name is Ehsan Amid, and in this talk I'm going to present LocoProp, which is a method to improve the performance of BackProp via local loss optimization. This is a joint work with Rohan Anil and Manfred Warmuth at Google. To review the problem, BackProp is the main method for training deep neural networks. Given a mini batch of examples, it involves a forward pass to calculate the pre- and post-activations of the layers. And then it proceeds by performing a backward pass to calculate the gradients. In this talk, we will denote by A hat the pre-activations and by Y hat the post-transfer function activations of a neural network. Then the BackProp update in the simplest form, gradient descent, can be written as applying a steepest descent direction, which is the negative of the gradient of the weights, which involves calculating the gradient via a chain rule. That is, the gradient of the final loss with respect to the pre-activations times the gradient of the pre-activations with respect to the weights. There has been numerous work to extend BackProp. These mainly involve decoupling the update across layers using synthetic gradients or augmented variables. But in this talk, we will mainly focus on first-order and second-order optimization techniques, which try to improve the steepest descent direction by applying momentum, exponential moving averages, preconditioning, and so on. Our main goal is to improve the BackProp step, which is gradient descent, by repeatedly applying local updates on layer-wise loss functions. Our construction is in a way that the first step always corresponds to BackProp. Therefore, taking further steps can be viewed as improving the initial BackProp step. Our construction is in a way that it's computationally cheap and memory efficient compared to second-order optimizers. The local updates are decoupled across layers and can be updated in parallel. And the local updates use first-order methods in contrast to second-order methods. It is applicable to any type of layer. And finally, it has lots of flexibility in terms of setting the local targets, loss functions, optimizers, and so on. Here we show two variants of our LocoProp method, namely LocoProp S for squared loss and LocoProp M for matching loss, or in other words, the Bregman divergence tailored to the transfer function of each layer. In both cases, given a mini batch of examples, the update proceeds by performing a forward pass to calculate the inputs to each layer. Then it proceeds by performing a backward pass to calculate a form of target. In the LocoProp S case, we calculate the targets by applying a gradient descent on the pre-activations, whereas in the LocoProp M case, we calculate the targets via mirror descent. After fixing the input and setting the targets, the update proceeds by repeatedly minimizing the local objective function. Here, inside the boxes, we show the gradient of the local loss with respect to the weights. In a benchmark autoencoder problem, we show that our LocoProp method significantly outperforms the first-order methods and provides a performance close to second-order methods, such as KFAC and shampoo. In terms of wall clock time, we provide significant improvement over second-order methods. Again, I would like to thank you for your time and listening to our talk. And if you are interested, here is a link to our paper. Thank you.